Nice to meet you.
Hey.
I'm sorry, guys. Yeah, traffic was terrible today, but hey, we know that 3 hours to get from Brussels is a bit extreme, even for me. So I'm very pleased to see you, Johan. Pleased to finally get here. Hopefully, I can have a cup of coffee after I ask you these questions.
No problem.
So I was sent all these questions in advance. So Johan, can you tell us what the PTZ project, what does it entail?
What we have a program here for tunnels around the Rotterdam area for a start, and we have to renovate our tunnels from scratch. The technical installations, we will replace all the 7 tunnels. All 7 tunnels are completely rebuilt. So we have now a chance to do things modern and different if needed. We try to get arranged some durability goals. This around in Rotterdam on the sheet, where several tunnels are located. We have one of the tunnels here, the North Tunnel, is the first one we want to do. But we have some ambitions about the durability, sustainability. Maybe the next sheet. 7 road tunnels, complete renovation for the electrical installations, and then our goals are next, please. But the main goal is less energy consumption. The tunnels are using a lot of energy, and we have now goals to reduce the energy with at least 50%, according to the normal ones. And we have that we're gonna hit that goal.
Mm-hmm.
The other one is less copper, less cables. We have to the renovation program. We have a lot of things to do, and to reduce the downtime of the tunnel. The less cables you have to run, the less time you have downtime you have. So we have different goals to reduce the number of cables, but also the copper. And I think we can do that also just by thinking now for advance. And the last one is that we want to reuse all the materials coming out of the tunnel. And that's one of the studies we are doing. Also, some other things we are doing is searching for energy storage, the energy transition parts, especially for alternatives for emergency power. We have now diesel generators. We are studying can we get rid of the diesel generators, modern technology, energy storage, energy. Sorry. But it's all energy storage and all that kind of goals we want to achieve. And we have a lot of questions about these subjects.
Mm-hmm.
That's very cool. One of the things we want to do is going to energy transition, storage, also. But how, what, where? So we had a study on this subject. We started with a program. The idea is to go to this kind of technologies. But how, what? And we had someone from TNO investigator for us. It's a bit in short of the goals of one of the main goals of the projects. And now we have here a presentation of Harry.
Mm-hmm.
Who will give a presentation about the study for the case North Tunnel to reduce energy.
Excellent, excellent. I mean, I'm fascinated and I'm looking forward to it. It does sound a lot of work, though, and particularly a lot of hindrance or congestion around. I've experienced that driving around the Rotterdam area this morning and through all the tunnels. So how do you do this, on these such heavily used roads? Because these are still working tunnels.
They're still working tunnels, and we are studying the possibility to place new equipment before getting rid of the old one.
Mm-hmm.
Because we're now trying to find a program to make some room in the tunnels to install new installations, test them, and get them into use. And then we are getting rid of the old installations. That's instead of that the tunnel was downtime for a year, we try to reduce it to several weeks, maybe a month. That's a goal we are working on, and all the studies we are doing now is to reduce the hindrance in the tunnel. The energy program, the less cables, as I explained, if you have half of the cables to be laid into the tunnel, it saves half of the time to run them, but also to test them, to all new installations installed. It's easier, it's quicker, we hope.
Mm-hmm.
A lot of that kind of works introducing 3D models so we can send a CNC robot the tunnel to make all the holes for the new installations. That kind of ideas we are working on this moment together with COB, several programs here.
Excellent. Sounds really great. And how is the project contributing to Rijkswaterstaat's or Netherlands' climate goals?
As I explained, the energy reduction, one thing, the materials used. We are now studying also, we have a lot of materials in a tunnel. When you know what in a tunnel now, we can also ask a question, why do we have a lot of things? One example is we have about 400 to 500 kilometers of cable in a tunnel. Why? And if we can get the cable out, do we have also all the new cables, are they needed or not? Rain, the problem with the traffic jam now was rain. We have some heavily rains also here, and how do you adapt to that kind of things? So we have to look into if it's rain, the pumps, are they big enough, storage big enough, all kind of investigation now, because we are now doing the tunnels are more or less halfway the life cycle. So we do installation, but also civil. The deformation of the tunnels, are they still correct? Will they run for another 50 years? That kind of investigation we are also running at this moment.
Sounds great. So this is all why TNO has performed this study?
Yep.
And is that what we're going to hear about now?
Yeah. They did a study about alternative, especially the case for the study for alternative energy storage and how does it fit into the tunnels, and also the how do you do with the regulations? We cannot be an energy producer, but how do we do our goals for getting the tunnels open within the energy transition market? A lot of questions asked, and a few of the questions will be answered by the study TNO did. So I will suggest to go to Harry.
So Harry, come in. I don't know where you're going to go. You're taking that space. So Harry, do you want to introduce yourself and kick us off?
Yeah, sure. So I have a laptop there.
Can you take the laptop?
Some pictures. I'm going to move up to this side. So thank you for inviting me, and thanks to everyone who's listening online. My name is Harry van der Weijden. I am a senior scientist at TNO in the unit Strategic Business Analysis. So we do studies not just into technologies, but particularly how technologies work in markets and business cases and environmental impacts and these kinds of things. And I have some slides to share with you, which I'm going to share now. So Konstantinos, if you can remove yours from the screen. It's still on mine, but let me see. Thank you. And you've already heard a little bit about background of the study, but just to reiterate what the question was that Rijkswaterstaat asked us. The question really was, Rijkswaterstaat has ambitious goals to be climate neutral in 2030, which really is not all that far away if you think about it, but also broader to provide a positive contribution to the broader energy transition in the Netherlands. And the question that we were asked is, what about energy storage? Can energy storage help to achieve those objectives? And how can it help to achieve those objectives? And what's the best way to do this? What technology should we use? What operational strategies? How should we use these storage facilities if we install them? And what is the resulting value to Rijkswaterstaat, but also what is the value to the broader energy system? So that's the question that we started with. I always like to start with the conclusions, because then you've seen the most important thing, and then I'll tell you something about the background. So the main conclusion is that energy storage in the setting of a tunnel can significantly increase the autonomy of a tunnel and the self-sufficiency of a tunnel. So these two things are not quite the same, so I have to explain what the difference is. So by self-sufficiency, I mean that energy storage can help reduce the use of the electricity grid, essentially reduce the use of the connection that the tunnel has to the electricity grid. And what you see in the left picture is that if you install local generation, so in this case we've looked at PV, if you install PV at the side of a tunnel, you can generate about somewhere between 30 and 40% of the energy that a tunnel needs, with that PV installation. This is a realistically sized installation, but even if you make it much larger, you're not going to get much further with just local generation. Simply because well, it's also night sometimes, and it's also sometimes cloudy, and even if you put some wind there, you can get that percentage up, but sometimes there is no local generation. So with only local generation, you can never be 100% self-sufficient. If you add, in this case, a realistically sized battery to this system, you can be over 70% self-sufficient relatively easily. And these are numbers for a typical Dutch tunnel, which we've calculated. So energy storage essentially doubles the self-sufficiency of a tunnel, so allowing you to generate most of the electricity that you need to run a tunnel locally. As you can also see, you don't get to 100%. So that's also an answer to one of the questions, is with energy storage, you cannot, with a realistically sized energy storage system, it's really difficult to make a tunnel 100% self-sufficient. That would require an amount of energy storage that is very large, but also uneconomical, because that last unit of storage, for instance, you would need once every 3 years. So you would barely use. So we concluded energy storage can significantly increase the self-sufficiency of the tunnel in combination with local generation, but not 100%. So realistic goals are important here. On the right side, we look at autonomy. So that is the average number of hours that the tunnel can operate if the grid connection is lost. With if I have that realistically sized battery and a realistically sized PV array. And we've looked at different operational strategies. I'll go into a little bit more detail later, but one of these strategies is just to maximize revenues with your storage. So that means you use your storage not just for the tunnel, but also to make money on the electricity market. That's shown in orange, and in blue, maximizing self-sufficiency. So really trying to maximize the amount of power from your own PV system that you use in the tunnel. And it depends a little bit on which strategy you use, but generally this realistically sized battery adds somewhere in the range of 8 to 12 hours of autonomy to a tunnel. So meaning a tunnel can operate even if the grid connection is lost. We see a difference between the different strategies, and I'll go into a little bit more detail later. There's especially a big difference in winter. So it's possible to combine these strategies to get the best of both worlds, to have a battery that significantly increases the autonomy of a tunnel year round, but also make some money on electricity markets. Going a little bit further, so energy storage can, as I said, contribute to autonomy and self-sufficiency of a tunnel, but also to the wider Dutch energy system. For instance, energy storage at the side of a tunnel can increase the efficient integration of renewables. We have looked also at business cases. There we have to conclude that if you just care about the cash, if you just care about the money that you make, from a purely financial perspective, energy storage is currently not very attractive. So you have to care about these other things. If you care about autonomy, if you care about self-sufficiency, then it starts to make sense. If you only care about how many euros you make, that at the moment for most settings in the Netherlands, it doesn't make sense. It doesn't cost a huge amount of money either, but it doesn't make you money. The technologies, batteries are, as we see it at the moment, the most appropriate storage technologies for most tunnels, unless there is a specific local opportunity to do something like pumped hydro or something else. But we don't see many opportunities for those kinds of technologies in the Netherlands. But then, of course, you have many different types of batteries, and there the best type of battery depends on the local requirements and the local constraints. So, for instance, is the battery going to be located in the tunnel? You have different requirements on fire safety, for instance, than if the battery is located outside the tunnel. So there's no kind of one size fits all, and you have to look at the local context here. And finally, so as I've already said, operational strategies can focus on self-sufficiency of the tunnel. So you can use a battery to make your tunnel as self-sufficient as possible, but you can also add value to the broader energy system at relatively little cost in terms of self-sufficiency. By making that capacity available in energy markets, especially in winter periods. So essentially doing arbitrage on electricity markets. So those are the main conclusions. Now just some background. So this project had 2 phases. In the first phase, we looked at what different value streams can energy storage bring, and which ones of those are really interesting. And we looked at the use of energy storage as emergency power supply for congestion, so local congestion management in the electricity grid, for use in balancing markets. but also for use on electricity spot markets and for an energy, what at that time we called the energy neutral tunnel. So can we use energy storage to make the tunnel energy essentially completely self-sufficient? And from that kind of first phase, we concluded that this energy neutral tunnel is probably not feasible just with energy storage. Definitely not energy storage in the form of batteries, but we can actually get quite far in that direction. So instead of focusing on this completely energy neutral tunnel, we broadened the scope a little bit to look at a highly storage to make a tunnel highly self-sufficient. And then, even though we took that as our main case, we also looked at if suppose you use storage for that reason, you build it for that reason, what other opportunities are there to help the broader energy system by making that capacity available on spot market. And in terms of technologies, we looked at a wide range of technologies, but focused especially on batteries. In the examples that I'm going to show, the costs are based on lithium-ion batteries. And then in the second phase, we looked specifically at this use case, so using storage to make a tunnel as self-sufficient as possible, but also using that capacity in energy markets. So the size, the storage that we looked at was sized to. So the reason for installing the storage was making the tunnel self-sufficient, but we also looked at these alternative strategies. So we have two strategies. First one is just minimize use of a grid connection. So I have some PV, I have some storage. My PV in principle goes to my tunnel. So the electricity I generate locally goes to the tunnel. If there is excess local production, I put that in my battery, which I can then later use in the tunnel. If there's no sun and also my battery is empty, then I use the grid to provide the electricity for the tunnel. So that's using the battery strictly to minimize the use of my grid connection. And the other use case we looked at is to maximize value on energy markets. And in that case, the battery is, so if I have sun, I am either providing that to a tunnel or I'm selling that capacity, I'm selling that energy to an electricity market, or I put it in my battery. And I also use my battery to arbitrage, for instance, between day and night or between evening peaks and troughs in electricity consumption in the morning. So here the battery is used not just for the tunnel, but primarily used to buy electricity when prices are low and to sell electricity when prices are high. And the first question then is, how big should this battery be? And we did a number of simulations for the Noord tunnel, so for a typical Dutch tunnel. And what you see here is the percentage here is essentially the percentage self-sufficiency of the tunnel. And we look at both power and energy capacity of a battery. What we see there is that if you can store energy for 6 hours with a sort of between 2 and 400 kilowatt power capacity, you can make this tunnel, this specific tunnel, so this is all real data, this specific tunnel about 72% self-sufficient. You can, of course, install a bigger battery. That doesn't really help you very much in terms of becoming more self-sufficient. You can also install a battery with a higher power rating. That also doesn't help you. That helps you a little bit because there are some hours during the year when there is an emergency and you have your entire ventilation system of your tunnel on. So that's why you go from maybe 72% to 73% self-sufficient, but that comes at a fairly major cost. So for this particular tunnel, this 340 kilowatt 6 hour storage capacity is the sweet spot. Definitely going much further than that doesn't seem to make a lot of sense because it doesn't bring you any additional self-sufficiency. So that's the capacity we're going to use for the rest of the analysis. So 6 hours of storage at 340 kilowatts. This tunnel, by the way, has a demand which you see here on a couple of days, which is slightly below 200 kilowatt generally, but it can peak much higher if there is an emergency. And here you see what happens if you install this battery in a tunnel on 4 days during the year. The easiest one is in December, if you have a cloudy day in December, basically almost all the electricity that the tunnel needs still comes from this grid connection in gray. There's a little bit of sun during the day, and that can feed directly into the tunnel, so that reduces your consumption, but storage doesn't really do very much here. In spring, on the 21st of March, you have much more sun in yellow in the middle. In fact, you have too much. So you store this in your battery. So it's the green, your production is higher than your demand. You store that and you can use that for most of the night, but not quite the whole night. So you still need your grid connection to supplement. But on sunny days, on the 21st of June and on the 21st of September, there is so much sun, in fact, that even if you put all of that in your battery, there is still excess. So in blue, you can still export some electricity to the grid. And you can store all the energy, basically, that you need for the entire night, unless there were no emergencies on these specific days. But so for normal operation, you can store enough energy to not need your grid connection at all. So this is all the self-sufficient strategy. So what if instead of using your battery to make your tunnel as self-sufficient as possible, you also try to make some money on electricity spot markets? And then it really depends which time of the year we're talking about. So if we're talking about winter on the right, as we've already seen, in winter, your battery doesn't do very much to help your tunnel be self-sufficient because there isn't a lot of renewable, locally produced energy to store. Because there is still some sun in winter, but you can use that directly in your tunnel. Your battery doesn't do very much. So in this case, if we tell the battery to make the tunnel as self-sufficient as possible, there's still a little bit, in blue, there's still a little bit of charge and discharge during different hours in the middle of the day, but not very much. So in winter, your battery is not doing very much to help you become self-sufficient, but there are big opportunities to use that battery capacity to make some money on electricity markets. And what happens here is that you store some energy at night, basically during the first hours of the day, and you discharge that during the evening peak between 7 and 8. And on the left, so here you have these two strategies not really in competition. In winter, you're not using your battery very much for self-sufficiency, so you can use it to contribute to market efficiency. In summer, it's different. So in summer here on the left, we see in blue, again, my self-sufficient strategies. If I want to be self-sufficient, I store all the solar that's produced during the day, so between 8 and sort of 3-ish, and I discharge during the night. On this particular day, again, this is real data. A market-driven operational strategy looks very different. So for the market-driven operational strategy, you store during the night when electricity prices are low, and then you discharge in the morning peak, so between 8 and 11, and you discharge in the evening peak between sort of 7 and 9. So the use of the battery is driven by electricity prices in the Netherlands, and not just by how much solar I produce myself, which is obviously not the same thing. So in the summer, these two operational strategies are different, and you have to choose what you care about. Do you care about being as self-sufficient as possible, or do you care about a market-driven approach? But during winter, these two are complementary. And when we do the calculations for the entire year, you can actually the revenues from a market-driven approach are highest in winter. So if you can use your battery capacity on energy markets a significant proportion of the time without really harming your self-sufficiency too much. Storage can also add autonomy. I've already talked about this and showing you this figure. So here I have two of them. On the left is the percentage of time that your PV system plus your battery can satisfy your tunnel energy demand for the next hour by month. And on the right, we're a little bit more ambitious and looking at the fraction of hours in which your system can satisfy tunnel energy demand during the next 4 hours. And this is data from real tunnel demand, so emergencies are included here as well. So the energy storage system together with your PV can in summer almost 100% of the time satisfy the energy demand of the tunnel for the next hour. And especially in June, also during the next 4 hours, so adds significant autonomy. And actually, in general, sort of 60 to 70% of the time, you can be autonomous, even if your grid connection, even if there's a fault in your grid connection, you can satisfy at least the next hour, allowing you to implement other measures so that you can keep your tunnel running even after that hour. Now, as I said, we did look at a business case as well. So here are some financial numbers. So there's 3 scenarios in this slide. There's a kind of business as usual, where we have nothing, we have no battery nor PV. There is a self-sufficient strategy. So we install this PV, this realistically sized PV array together with my battery. And I use that to only use the battery only to increase self-sufficiency. And then a scenario where I install that same capacity battery, but use it to make as much money as I can on electricity markets. So that kind of 2 extremes. We haven't looked at a combination here. And on the top, you see energy costs. Obviously, if you install some PV, even just the PV, but the PV plus the battery, your energy costs decrease. If you install a battery and you use that to make some money on electricity markets, your energy costs, in fact, become revenues rather than costs, because you're trading energy. So you see here that energy storage combined with local generation reduces your energy cost, can even eliminate them altogether. But of course, these systems are expensive, they cost money. So if I include those on the bottom, I have net present value over 15 years. And there I see that, of course, my business as usual, it still costs money to do things as we do it currently. We still need to pay for our energy. But if we go to the self-sufficient strategy, and I see I haven't translated my heading here, but the second one is still self-sufficient, that has a lower MPV. So even though I save energy costs, that doesn't quite offset the cost that I have to make to buy my battery and my PV system. Now, it's not a huge amount. This is 10 million over 15 years. Especially on the scale of things, what the typical cost of a tunnel renovation is. This is not large, but it does mean that if it's just the MPV that you care, if you just care about the euros, installing a battery and using that to become self-sufficient does cost additional money. If I can recoup some of that by using my battery, especially in winter, to trade electricity on markets, but that doesn't quite get me to a higher MPV than if I do nothing. Now, this is just for the revenues that we're looking at here is just spot markets. It's possible, depending on the jurisdiction that you're in, but in the Netherlands, it's possible to also use your storage on imbalance markets. We haven't have that on the slides. We did look at this. This can make your business case better, but not quite enough to achieve an MPV that's really higher than the business as usual case. So there's still not enough money to be made, even in imbalance markets, to make sense. And being active on imbalance markets also means that storage capacity cannot be used for something else. So it also comes with more significant disadvantages than just using it on spot markets. Another caveat is that there might be opportunities for local congestion management. If your tunnel happens to be in a place where there is local congestion that is also expected to remain there for some time. But this depends on, and in that case, you might have a positive business case, but that really depends on where you are. And this you'd have to discuss with your local system operator. These opportunities for congestion management are unlikely to be there forever, because if there is sustained congestion during a long period of time, at some point your network operator will probably upgrade the network. So there's a question about how long you can access these benefits, but upgrades to distribution networks can take a very long time. So if there are opportunities to do this locally, this might help. And another complication here is that if you are already renovating a tunnel, and you are, for instance, already installing a new UPS system, that is an energy storage system, you might, instead of having to install an additional energy storage system, you might just install a larger UPS system. And use that capacity not just for emergency power supply, but also to deliver some of these other services. In that case, there is an obvious synergy. You don't need to buy a second device, but you buy a larger first one, which means that costs might be lower. That we haven't assessed here. So, conclusion again is that investing in energy storage, especially if you're already renovating a tunnel, can make sense if you care about things like autonomy or self-sufficiency. It's important that set realistic goals So don't think that energy storage is this kind of silver bullet that can make you absolutely climate neutral, self-sufficient and everything, but it can help. But it's important to set these to be realistic about this, and therefore also not to discount technologies that can maybe not get you to 100%, but can get you to 70%. Look for operational strategies that combine private and public benefits. So for this particular tunnel, we saw opportunities there to do something else in winter than you do in summer, allowing you to not just be self-sufficient, but also to help the broader system without these two things really being in opposition. Talk to your distribution network operator, to your distribution system operator, and use local opportunities for instance, congestion management if those are there. But talk to your DSL anyway, because if you're doing anything to change the use of your connection, they probably want to know. And there's no one size that fits all. So choose a technology and a capacity that suits an individual tunnel. The energy demand profiles are not the same. Locational constraints and opportunities are not the same. Electricity networks are not the same. So there's no do your homework well for the particular tunnel that you're renovating. And then finally, some other lessons that we learned through doing this project, which were not in our initial brief, but which I thought were interesting to look at. And these are some more kind of fundamental questions that I think are important to ask yourself if you are looking at energy storage in these kinds of applications. So first, if you discuss the role of your organization early on. So for an organization like Rijkswaterstaat, which is a public body, at the end of the project, I think we started to have discussions about so what if we make money on electricity markets? Is that our role, or is that even allowed? Should we want to become energy neutral? But should we really? Should we be more ambitious? Should we play an active part in this energy transition, or are we just energy consumers? And are we just looking at the physical infrastructure, but not at the electrical infrastructure? I think that's an important question to address if you are an organization that's not a traditional energy company. What do you actually want to do? And what do you want? Do you want to minimize the costs to yourself, or do you have broader objectives? And if you have broader objectives, what are they? Also, are you going to invest yourself, or are you? And what happens if you do that? So, for instance, as Rijkswaterstaat, if you build batteries and you start to become active on electricity markets, you are changing market dynamics, which might make it less attractive for commercial parties to come along and to do something similar. Is that okay? And how do you make sure you're not just crowding out commercial parties from a market, but that you really contribute? Second is ensure that you know why you're doing this. So why is self-sufficiency? Why is that important? And autonomy. Why is that important? And what does that mean for your target? So we started out in this project looking at 100% self-sufficiency of the tunnel, because we thought that was what was important. And through working together and through looking at different variants, we discovered that maybe 100% was nice, but 70% was also really good. Because we don't care about self-sufficiency as a sort of absolute number, but this is it's a probabilistic metric. So ensure that you know why you're doing, why you're looking at energy storage, but also why you care about the metrics that you defined. And finally, get clarity on regulatory constraints and the scope for discussing changes to these. So in the scope of this project, for instance, we talked a lot about reliability levels. So how reliable does a tunnel actually need to be? And is it maybe okay if it's a little bit less reliable, if that's a lot cheaper or a lot more sustainable? And are there maybe practices that are current practices but not strict legal requirements? So it's important to get clarity of these. The second one I've already mentioned. Can as a public body, are you allowed to participate in energy markets? Which energy markets are you allowed to participate in? What happens to the revenues? Are they taxed differently from other things that you do? This all really matters for whether you use energy storage, but also how you use it. And I'm sure there's many more of these questions that you need to ask yourself. But this I find the most interesting part of the project, as these kind of meta questions where within the organization, I think we started to think about why are we doing this, and can someone else do it, or should we? And if anything, I think these are more important than the actual numbers, because the numbers you need to look at for an individual tunnel anymore. Perfect. That's all I have for you today.
Q&A. Okay. Thank you, Harry. So,
sharing
yeah,
this.
do you want to come up here? I think now we can have an interactive Q&A. I was. I don't know what the. You need to get in shot.
I see the picture.
Yeah, we see the picture. That was. I think one of the first things I'm struck is understanding some of the terminology, because I must admit, at one point you started talking about congestion. Okay, from the roadside, I thought I knew what, but yeah, what you're basically talking about is under capacity of the local electricity network.
Yeah, I don't like it. I don't like it under capacity because simply you would never build a road that's never congested, because then you build the last lane for that one car a year. That's right. It's the same in electricity networks.
Okay.
So it's the same problem. Sometimes there's too much power that's trying to get through, and you have to somehow deal with this. There's no traffic jams in electricity networks. Unfortunately, what happens is that lines get hot and stretch and break.
Yeah.
So you have to avoid this. But still, congestion is a natural part of an electricity network. It will never go away. But if it's present somewhere all of the time, you probably want to build that extra lane.
Yeah.
But if you have a tunnel with a large electricity demand which is flexible, you can maybe help your network operator and say, during these few hours of the year when there's so much wind, coming through here, I'll reduce my electricity consumption a little bit, so you don't have to upgrade your network.
Okay. I guess I'm looking at you as well, because one of the things I'm also struck by, again, as road operators, unlike I think many of the other people trying to get into this sector, because there are people who think they can make money on it. But one of the benefits of a road operator is you are national. So when you talk about your congestion management and that kind of thing, are there actually different strategies you might do, because you have 15, 20 different tunnels dotted around the country that would lead to different discussions with the network operator than it would if it was isolated?
Yeah, sure. Yeah. Because the local distribution are several companies, and you can have windmills in northern Netherlands. You have not the power here in Rotterdam. So the grid, national grid, is also part of it. But the tunnel are mostly in congested areas. So near Rotterdam, you can have a temporary problem for the congestion. You might be able to say for the next 4 hours, I will not use energy from your grid, so the energy can go to the hospitals or the cars or the other things. And that's the main goal of the idea of the storage. If I'm able to disconnect the tunnel for some time from the grid, I can help other operators for energy, the energy grid. One of the things we are looking at is not the main goal. The main goal is to have safe and available tunnels. That's our first part, but there are possibilities to look somewhat broader, and that's why we are a public company. We are from the government, so we might consider to help our colleagues from the grid a bit. But the main goal for the tunnel is have a safe tunnel, available tunnel, and that's the discussion we learned also here. Where do we stop? How much money do we invest, and where can it help other people also?
I think that's an important point. And again, I go back to the terminology. Yeah, when you talk about autonomy, because that, if you're in this just to what was the term you used? Your market-driven approach. Okay, you're buying the cheap electricity, you're using the when it's expensive, but that would kind of drive you to a strategy where you might as well just invest in one big place.
Yeah.
But the focus on autonomy actually means you have to have a distributed network. And the question is, okay, how do you use the advantages of that rather than the advantages of scale, which would lead to the so how do you cost that in? I guess that's what I'm interested in. How do you cost that in? That actually because there was a question about the value. How do you value autonomy in your calculations versus?
It's not only about money. The main goal is if a tunnel is not operating because there is no power, we have a traffic jam.
Yeah.
And we have a traffic jam in Rotterdam. It costs the society a lot of money. Lots of I don't have to tell you. So the first consideration we made is I have to have a tunnel which is available. And now we invest a lot of money in diesel generators, in UPS systems and all that kind of thing to have this tunnel as long as operated as possible. Sometimes we have even second grid connections. to have this tunnel operated. But if I'm able to have a storage in a tunnel which is flexible for a lot of hours, 1 hour, 4 hours, maybe even longer, I can have, if there is a problem with the grid, sometimes it fails, I have the tunnel open. So the traffic can go on, the emergency services can go on. There's also a part which is not to express in value in euros, but in other value. Dus part of this investment we have to do is also about having this tunnel available. We have a nice example in Vienna with Asfinag, with also this network they are building now for the city to be available and connectable if there are problems. Our tunnel, every tunnel has its role, but if we are able to connect these tunnels, the distance in Rotterdam are not too big. If we connect them some way, that's more future. We can have also the problem if there is a real net failure. We can have the infrastructure also still available.
If I can add to that, I mean, you can try and convert some of these things that you've just mentioned to money. The travel times, there are standard methods to convert travel times to money. I don't think I'm an economist, right? But even as an economist, I say I don't think that's always helpful. And it is helpful to look.
You said that an economist said it's not always helpful. Okay.
No, I mean it's sometimes helpful to try to sum all the effects.
Sure.
But different people care about different effects. There are always things that you can't quite, your reputational damage, for instance, if your infrastructure closes, how do you convert that to money? So there's always a temptation to try and do it and to convert everything to money, but that sometimes that's a good thing to do. But it's also helpful, I think, to have these metrics separate and to say, okay, maybe in monetary terms, this is costs a little bit of money. Still, if it costs a lot of money, it's still a different question than if it costs a little bit of money, right? But there are all these other benefits that we think on balance we should do this. But I think it's important to provide decision makers with kind of different metrics and not just try and bring everything down to euros, because that just oversimplifies.
Going back to or adapting one of the questions on the screen, because I mean I think we've all heard about energy storage for electric vehicle charging. We can hear about it here for tunnels. What are the differences between those approaches, and what about other infrastructures? It mentions locks and bridges. How do you see that? Are they the same strategies, or are there subtle differences between them?
I think energy storage can do a lot of different things. The European Association for the Storage of Energy has a taxonomy of, I think, 20 to 30 different value streams for storage. Most of them don't apply to the tunnel context, but so there are a lot of different things that storage can do, from very short term, keeping the frequency of the grid correct, to very long term, summer to winter storage, and your technology obviously depends on what you're trying to do. Tunnels are particularly nice for storage in combination with PV, because tunnel electricity demand correlates with solar production. Because if the sun shines, then your lights at the entrance of your tunnel need to be brighter, so that people are don't suddenly experience a change in brightness as they drive into a tunnel. For the North Tunnel that we looked at, that correlation I think was about 30%, which is normally it goes in the other direction. If you look nationally, solar demand is negatively correlated to demand, because we use energy when we cook, and in the morning and in the evening when it's not very sunny, and we're not at home during the afternoon. So therefore, this PV for tunnels is really interesting. It's a really interesting use case, and that makes storage also very interesting, because you just need less storage to become autonomous. I think this probably applies to some other infrastructures as well. The other characteristic of tunnel, of course, is that the electricity demand on average is lowish. We saw kind of 200 kilowatt, but the connection size is huge. Because when everything is on, when there is an emergency during the night, and you then suddenly, this particular tunnel has a connection of nearly 1 megawatt. It's 5 times higher than more than 5 times higher than your average consumption. So you have all this kind of unused capacity sitting there, which also makes storage interesting, because then maybe you need less capacity, or maybe you can use that to transport some electricity back to the grid, so there's also this kind of opportunity there to use something more efficiently. I think that many infrastructures will share that, even rail infrastructure will share that, and definitely things like locks or bridges.
especially bridges, because bridges are used for several minutes. When the bridge is opened and closed, they use energy, and the rest of the time not.
Yeah.
And you have this big connection you're using for several minutes a day. It's very costly investment for the grid. If you can run the bridge from storage and load the battery slowly, you can reduce the connection to the grid a lot. And especially for bridges which are further away from the areas. We have some bridges in parts of the Netherlands are in the middle of nowhere. There's a lot of expensive infrastructure to get energy there, and this infrastructure we use only for a small part. So we have a smaller connection. It might be a solution also.
And I like your mention of the PVs and the brightening, because I guess that would also apply to some of the signage we see on motorways, where we might want to make the signs brighter when the sun is shining. Actually, we have to have it on.
I think can I add one more thing here, because I think there's one other important one that all these infrastructure share is just there is space. And space is something, especially in the Netherlands, we don't have a lot of. And the space is becoming, in the energy transition, is becoming a main constraint. We have to put substations in industrial areas where there is no space, and this is already starting to become a problem. And we've only just started. Tunnels and bridges and locks, and they have lots of space. So if we need to and we need energy storage, of different types and different durations, and so this again makes all these infrastructures interesting, because there we have space. We can't really use that we can't grow anything there, or we can't put buildings, we can't house people there, but we can put containers there, for instance. So that is, for me, is another interesting.
So you heard it first. We're going to be using batteries as noise barriers. Okay, but move on to another thing that was mentioned. I'm interested in the business models, because this also comes down to the mandate, and you touched on it, the mandate of a road authority. So when we talk with the different NRAs around Europe, some are very reluctant to get into this space because they feel that they're not allowed. Sometimes they're explicitly told they're not allowed. How do you see that developing? Do you see maybe there's new business models, or do you have to? Does it call for public-private partnerships, and are those existing?
I think things change. It's changed a lot. When you look at the situation 5 years back, this energy transition was not hot, it was not needed. Now we are some years further. Things are changing quick, and I think we should reconsider what we did always in the past, or reconsider for the future. I think the aspect of the space. We have also programs here in the Netherlands that space from alongside the roadways are used for energy production, or are some programs running. Discussions also, are we a government for road authority, or are we energy supplier? That discussion it is needed, but I think that there must be somewhere decision about what the role of the Rijkswaterstaat is. We are for the roads and the waterways, and not for energy. We have other companies for that, but I think we have to connect in one way and work together in solution for the energy transition. And I think we have to look over our boundaries and try to find each other at some point. And that might be needed to change some cost range. It might be, but the discussion, we have to get to the discussion quick. I think.
Thank you. Great. So there's a specific question: how many panels would you need? You said we've got lots of space.
Oh, that's a good question. So for this particular case, I don't remember how many panels we put on. We did check whether it would fit, and that was not a problem at all. These are large structures.
Okay.
And the solar panels have become a lot cheaper and more efficient. So I don't think you have more space than you need.
Okay. And going on to the batteries, because this is something I've heard before. So that there's this. Is there a competition between the materials we need for the storage and the car batteries, which of course we want to have, or even, and I've seen that, where the big batteries for storage actually use recycled or old car batteries. How do you see that balance? Is that a real issue, or?
No, it is, especially the environmental effects, I think, of your battery technology you do need to consider. And that might mean, for instance, that you choose technology which is maybe slightly more expensive, but doesn't use lead or whatever materials that are environmentally damaging. And yes, materials availability is an issue, but also storage technology is developing very quickly, and we have new technologies coming along almost every year. Prices are coming down very quickly, so I'm optimistic. I think that. Consider the environmental effects and consider where these things are produced as well, and are you becoming dependent on places that you'd rather not become dependent on? Let's not replicate our current energy system, the problems that we have with our current energy system again. But I'm optimistic that technology still, it's going in the right direction. We have technologies now which use much less rare materials, and especially if you have the space. As you have for infrastructures, you might choose technologies that are maybe less energy dense, so take up more space, but use even new technologies that use seawater or similar.
Mm-hmm.
So I think we can manage.
Great.
But yeah, do consider, don't just look at your own backyard, but where does all the kit that you're installing actually come from, and kind of that when you do your environmental assessments, include those.
Okay. And back to Tim, you had a slide, you talked about the imbalance market or something like that. And you said we haven't really, but what is the imbalance market? Sorry for being so dull.
No. That's perfectly fine. So I'm an energy economist at heart. So electricity supply and demand has to be in balance always, on a second by second or even millisecond by millisecond basis. Otherwise, the lights go out. But of course, energy demand and energy production are not perfectly predictable. They're very, very predictable at short terms, but not 100.000%. So there's always a need for some capacity that can respond very quickly. So that if we switch on the light here and increase energy demand in the Netherlands, nobody could have predicted that. So there needs to be some capacity available which can respond very quickly to unexpected. So things that an hour ago were not expected yet. Suddenly the wind goes down. Some clouds that were not predicted, demand suddenly goes up. So there, most countries will have an imbalance market. So this is capacity that's procured ahead of time. So you're usually a network operator will operate some market and say and ask for this capacity. Say who's able to help me if there is an imbalance. And in order to bid in these markets, you have to have capacity which is available at very short notice. And there are usually several markets. So some markets have very, very short notice that are automated. So that means you essentially give your system operator a button that they can press, and then your battery, for instance, starts to charge or discharge.
Under their control. So that's the point.
So that's the very fastest, but there are also slightly slower markets where you can control, but you have to still be able to respond within, say, 5 minutes or 20 minutes.
Right.
So these are the very short-term electricity markets that are procured ahead of time, and then so we sort of looked at them and said, okay, there's money to be made there, obviously, if you have something that can respond quickly.
And if you have the scale of something like Rijkswaterstaat.
Yeah, you don't even need scale anymore. There are aggregators that aggregate several smaller facilities, so that's not an issue. Prices are generally high in these markets at the moment because not everybody can provide this. Not everybody can. If you have a wind turbine, this is already a lot more difficult. You can reduce your production, but you can't increase it usually.
Yeah.
And with a battery, you can do both. But this comes with disadvantages because if you are paid to be available, you have to be available. In an electricity market on an hour-to-hour basis, if you sell some energy, you can always buy it from someone else and resell it if you really at that moment don't want to produce. But for imbalance markets, there is a requirement, which means, for instance, you can also use this as an emergency power supply.
That's the interesting part where we are not only for my tunnel, the operation of my tunnel, but might be interesting to look over the boundaries and help the society in the broader. And that's the discussion we are now. Are we from our tunnels or are we from society? And somewhere there, the discussion has to be made now. And we have to talk about it and see what we are going to do and how much, if there is space available, space around the tunnel and there is a big city around it where there's no space available, can we provide services not only for our tunnel, but also for the cities, for grid connections, all that.
course, you can
It's-
still decide to make a space available to someone else,
Yeah.
to a commercial party who can.
That's
So
part-
still,
partly our
how much do you want to
job.
do yourself?
That's a great one, because I love this one where we say, you know, this is not just about protecting the road infrastructure. Of course, that's your main job, but actually looking over the fence, the noise barrier, or
And-
whatever, and saying, well, actually, we have this societal role, and we can't, you know, prioritize the road over society, because the road is part of society.
Well, it's interesting discussion now, and we started this study October last year. And October last year, there was very not do it. And now we have more open, and there is interest for this subject and also discussions. And now we see within half a year, also the world is changing now. The old people are talking about what do we have to do. So the discussion is open, I think.
Excellent. Right. Well, with that, because I'm looking at the clock, yeah, we've run out of time. I'm really sorry for that. It was really good to talk to you. I hope we're going to go offline now, and we're going to talk again, because I think this was really, really good. An excellent input, and of course, a very, very topical issue that I know many road authorities are looking at. You heard mention of Aspenag, and I know others are also looking at as well. So I hope we can come back to this very topic, maybe in a few months' time or something like that, because I'm sure it's going to develop very, very quickly, and there's a lot going on.
There was some addition from Brussels though, to conclude this session.
There was an input from Brussels?
Yeah.
Sorry, okay.
There was some last sheets we discussed when you were
Right. Hey, this is when we go live.
not close. Continuous is
Yeah.
closed down.
So just to see the next events and webinars for you to have a look at. So just if you. if you-
Okay,
if you
yeah,
have a
thank you,
look at
Constantinos. So
next
thanks,
events.
Constantinos. Just reminding everyone, these are the webinars coming up. You know, some environmental issues, other issues. I guess we're already running down for the summer. So, but there will be more coming, and I'm sure we'll come back to these topics and many, many others. So tune in to the CEDR webinars in the future. Other than that, have a great rest of the day, and see you all soon. And thanks, guys. Thank you.